in this lecture we'll find out the distance between the centers of two circles. In the drawing we have rectangle ABCD. We know that side AB of this rectangle is equal to 7 units in its length. Side BC equals to 24 units. Inside this rectangle we have those two circles. The center of this circle is here at point Q, the center of this circle is here at point P. Our mission is to find out the distance between the centers of those two circles, that is to say, the length of the line segment QP. Okay, so first of all, because of the fact that ABCD is a rectangle, it means that all those four angles are right angles. So I write it down. Okay, this angle equals to 90 degrees. This angle also equals to 90 degrees. This angle equals to 90 degrees. And finally, this angle is also equal to 90 degrees in its side. In addition, we note that the opposite sides of a rectangle are equal to each other. That is to say, side AB equal to side DC. But AB is 7, therefore DC must be also equal to 7 units in its length. So write it down. So this side DC is equal to 7 units in its length. Likewise, according to the same rule, side BC must be equal to the opposite side AD. But BC is 24, therefore AD must be also equal to 24 units in its length. In the next step, we'll implement the Pythagoras theorem on the right triangle ABC. Okay? So in the right triangle ABC, by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of the right triangle ABC is AC, therefore the square of the hypotenuse is AC squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AB squared plus BC squared. Repeat again. According to the Pythagoras theorem in the right triangle ABC, AC squared equals to AB squared plus BC squared. So AC squared, that is the square of the hypotenuse, equals to AB squared. AB is 7, therefore AB squared is 7 squared, that is 49, plus BC squared. BC is 24, therefore BC squared is 24 squared, that is 576. So we can know that AC squared in total is equal to 49 plus 576 is 625. So AC squared equals to 625. We will take a root out of this equation, and finally we get that AC equals to the square root of 625 is actually 25. So we actually found out that the left of the hypotenuse AC, the right triangle ABC, is equals to 25 units. So I'll write it down here. AC equals to 25 units in its length. So the right triangle ABC blocks this circle, while the right triangle CDA blocks this circle. So in the next step, we will develop a new formula that will help us to find out the radius of any circle that is blocked by the right triangle. So here we have the right triangle ABC that blocks this circle. We will define the radius of this circle as x. And we will develop a new formula that will help us to find out the value of x only by knowing the side lengths of the right triangle ABC that blocks this circle. Okay? We will define the point of tendency of tangent BC with this circle. This point is point M. OM is the radius of this circle that is equal to x according to our definition. The radius OM is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Tangent AB is tangent to this circle here at point M. Point M is the point of tendency of tangent AB with this circle. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to this rule, rule number 1. So if we can implement rule number 1 in our drawing. So we define the point of tendency of tangent AB with this circle as point N. We join points O and N together by a straight line. ON is the radius of this circle that is equal to x, according to our definition. So the radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So inside quadrangle ONBM, we have 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of this fourth angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing fourth angle here must be equal to 90 degrees. Again, in order to complete the sum of the angles in this quadrilateral ONBM to 360 degrees, the missing angle here must be equal to 90 degrees. So, we actually found out that inside this quadrilateral NOBM we have 4 right angles. Therefore, we relate to this quadrilateral NOBM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side NO must be equal to the opposite side BM in rectangle NOBM. But NO is X, therefore BM must be also equal to X. Likewise, in the same rectangle, side OM must be equal to side NB. But OM is X, therefore BM must be also equal to X units in its length. So we actually found out that quadrilateral NOBM is not a rectangle but a square one because of the fact that all of its sides are equal to each other. Each side of this square is equal to X. What is the length of this line segment AN? From the moment it is very easy to see that AN equals to AB minus NB. Again, AB minus NB equals to AN. So AN equals to AB, that is A, minus NB, that is X. So in total, AN equals to A minus X. I'll remind you that according to our definition, the length of side AB is A units, side BC equals to B units in itself. And finally, the length of the hypotenuse AC of this right triangle ABC is equal to 3 units, according to our definition. So, what is the length of this line segment CM? From the moment it is very easy to see that CM equals to CB minus MB. Again, CB minus MB equals to CM. So CM equals to CB, that is B, minus MB, that is X. So in total, CM equals to B minus X. So write it down. CM equals to B minus X. So in conclusion, we found out that AN equals to A minus X, while MC equals to B minus X. Okay, so here we have also rule number 2. First of all, we define the point of tendency of tangent AC with this circle as point S. And here we have rule number 2. According to rule number 2, the lengths of 2 tangents from a common standpoint to a circle are equal. We have the common standpoint point P. From the common standpoint point P, we have 2 tangents to this circle, tangent PA and tangent PB. According to this rule, rule number 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement rule number 2 in our drawing. Why? Because in our drawing, if we focus on the common standpoint point A, from the common standpoint point A, we have 2 tangents to this circle, tangent AN and tangent AS. And according to rule number 2, they are equal to each other. That is to say, AN equals to AS. But AN is A minus X, therefore AS must be also equal to A minus X. Likewise, we focus on the common standpoint point C. From the common standpoint point C, we have 2 tangents to this circle, tangent CM and tangent CS. And according to rule number 2, they are equal to each other. That is to say, CM equals to CS. But CM is B minus X, therefore CS must be also equal to B minus X. So write it down. In conclusion, we found out that AS equals to A minus X, while SC equals to B minus X. So, AC is the hypotenuse of the right triangle ABC that is equal to 3 units in its length. from one side, but from the other side, the hypotenuse AC is also equals to AS plus SC. So we can write here that C also equals to AS plus SC. That is to say, the hypotenuse AC that is equal to C, according to our definition, is equals to AS. AS is A minus X plus SC. SC is B minus X. So in total, we found out that the hypotenuse AC of the right triangle ABC equals to A minus X plus B minus X. That is to say, C equals to A plus B minus X is minus 2X. So C equals to A plus B minus 2X. We will add 2X to this equation and we get that 2X plus C equals to A plus B. We subtract 3 from this equation and we get that 2X equals to A plus B minus C. We divide this equation by 2 and finally we get that X equals to A plus B minus C over 2. So I actually succeeded to find out a general formula for the radius of any circle that is blocked by the right triangle, triangle ABC. So the radius of this circle that is equal to X according to our definition equals to A, that is the length of side AB, plus B, that is the length of side BC of the right triangle ABC, minus C, that is the length of the hypotenuse AC, over 2. Again, the radius of this circle that is equal to X, according to our definition, equals to A plus B minus C over 2. Now we will use the new formula in order to find out the radius of this circle. We find out the radius of this circle that is blocked by the right triangle, triangle ABC. So first of all, we define the radius of this circle as R. Again, the radius of this circle equals to R according to our definition. Now we will implement the new formula in order to find out the value of R, that is the radius of this circle, that is blocked by the right triangle, triangle ABC. So R, according to the new formula, must be equal to AB plus BC minus the length of the hypotenuse, that is AC, over 2. Repeat again, the radius of this circle that is equal to R according to our definition, and this circle is blocked by the right triangle, triangle ABC. According to the new formula, the radius R equals to AB plus BC minus AC over 2. AB is 7 plus BC, that is 24, minus AC, that is 25 over 2. 7 plus 24 is 31, minus 25 over 2. 31 minus 25 is 6, and 6 over 2 is 3. So finally we found out that the radius R of this circle is equals to 3 units in its length. Likewise, we'll implement the new formula on this circle that is blocked by the right triangle, triangle CDA. We define the radius of this circle as X. The value of X, according to the new formula, again, this circle is blocked by the right triangle, triangle CDA. So the radius of this circle X must be equal to CD plus DA minus the hypotenuse CA over 2. Repeat again. The radius of this circle X, according to the new formula, must be equal to CD plus DA minus CA over 2. CD is 7 plus DA is 24 minus CA, that is 25 over 2. 7 plus 24 is 31, and 31 minus 25 over 2. 31 minus 25 is 6, and 6 over 2 is 3. So finally we found out that X equals to 3 units in its length. That is to say, the radius of this circle X is equal to 3 units in its length. In the next step, we define the point of tendency of tangent BC with this circle SM. PM is the radius of this circle that is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MP. According to rule number 1. That is to say, this angle equals to 90 degrees, this angle also equals to 90 degrees. In the next step, we define the point of tendency of tangent AB with this circle as point N. We join points P and N together by a straight line. Pn is the radius of this circle, that is equal to 3 units. The radius Pn is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to the radius NP, it means that this angle equals to 90 degrees, and this angle will also equal to 90 degrees according to rule number 1. So inside quadrilateral PNBM, we have 1, 2, 3 angles, therefore the fourth angle must be also equal to 90 degrees. So inside quadrilateral PNBM, we have 4 rectangles, therefore we can relate to this quadrilateral PNBM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side NP equals to side BM. But NP is 3, therefore BM must be also equal to 3 units in its length. Likewise, according to the same rule, in rectangle PNBM, PM equals to NB. But PM is 3, therefore NB must be also equal to 3 units in its length. So we actually found out that quadrilateral NPBM is not a rectangle but a square. Why? Because of the fact that all of its sides are equal to each other. Each side of this square is equal to 3 units in its length. If we repeat on the same process on this circle, we'll get here that here we also will have a square that is identical to this square PNBM. So here we will define the point of tendency of tangent AD with this circle as point G. QG is the radius of this circle that is drawn to point G, that is the point of tendency of tangent AD with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius GQ. That is to say, this angle equals to 90 degrees. this angle will be also equal to 90 degrees according to rule number 1. Likewise, we define the point of tendency of tangent DC with this circle as K. We join points Q and K together by a straight line. QK is the radius of this circle that is equal to 3 units. The radius QK is 1 to point K, that is the point of tendency of tangent DC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius QK. If this is perpendicular to QK, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. So inside quadrangle QKDG we have 1, 2, 3 angles, therefore the fourth angle must be also equal to 90 degrees. So inside this quadrangle QKDG we have 4 right angles, therefore we can relate to this quadrangle QKDG as a rectangle, and we also know that the opposite sides of a rectangle are equal to each other, that is to say QK equals to DG, but QK is 3, therefore DG must be also equal to 3 units in its length. Likewise, according to the same rule, in rectangle QKDG, side QG must be equal to side KD, but QG is 3, therefore KD must be also equal to 3 units in its length. So again, we actually found out that quadrangle QKDG is not a rectangle but a square. Why? Because of the fact that all of its sides are equal to each other. Each side of this square is equal to 3 units in itself. So we actually found out that those two squares are identical to each other. Each side of those two squares is equal to 3 units in its length. Okay. In the next step, we'll extend the radius GQ of this circle until it touches side BC. We will define the touching point of the extended radius GQ and BC as point T. So by doing this construction, by extending the radius GQ by a straight line, we created here the big quadrangle TC DG. Inside this big quadrangle TC DG, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. So actually found out that inside the big quadrangle GDCT we have 4 right angles. Therefore we can relate to this big quadrangle GDCT as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side GD must be equal to the opposite sides TC. But GD is 3, therefore TC must be also equal to 3 units in its length. Likewise, according to the same rule, in rectangle TCDG, side DC must be equal to side GT. But DC is 7, therefore GT must be also equal to 7 units in its length. GT must be also equal to 7 units in its length. In the next step, we will extend the radius LP of this circle that is equal to 3 units by a straight line until it touches side DC of rectangle ABCD. The radius of any circle, it is absolutely a straight line. And when you extend a straight line by straight line, the result must be a straight line. We define the touching point of the extended radius NP inside DC of the rectangle is point Z. Again, we extended the radius NP by straight line, and the result is NZ. Therefore, NZ must be also a straight line. So NZ is a straight line. By doing this construction, we actually created here for the big quadrilateral NBCZ. Inside this quadrilateral NBCZ, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So inside the big quadrilateral NBCZ, we have 4 right angles. Therefore, we can relate to this big quadrilateral NBCZ as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side NB equals to side ZC. But NB is 3. Therefore, ZC must be also equal to 3 units in its length. Likewise, in the same rectangle NBCZ, side BC must be equal to side NZ. But BC is 24, therefore NZ must be also equal to 24 units in its length. So I write it down here that NZ, this side NZ of rectangle NBCZ must be equal to 24 units in its length. We will define the intersection point here. We will define this intersection point as point Y. And we will focus on the small quadrilateral YZTC. Inside this small quadrilateral YZTC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So inside the small quadrilateral YZTC, we have 4 right angles. Therefore, we can relate to this small quadrilateral YZTC as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side ZC must be equal to side YT. But ZC is 3, therefore YT must be also equal to 3 units in its length. Likewise, in the same small rectangle YZTC, TC must be equal to YZ, but TC is 3, therefore YZ must be also equal to 3 units in its length. So I actually found out that the small quadrilateral YZTC is not a rectangle but a square. Why? Because of the fact that all of its sides are equal to each other. Each side of this square is equal to 3 units. So therefore we can say that we have here 3 identical squares, 1, 2, 3. Each side of those 3 squares is equal to 3 units in its length. Okay, again, we extended the radius ZY. We extended ZY by a straight line, and the result is Zn. When you extend a straight line by a straight line, the result Zn must be also equal to, must be a straight line. Okay, so Zn is a straight line that is equal to 24. So Zn, that is a straight line that is equal to 24, minus Zy minus Pn, in total it must be equal to the missing side, side Py. So I write it down. The missing side, side Py, must be equal to Zn, that is 24, minus YZ that is 3 minus PN that is also 3. Repeat again, the missing side PY. From the drawing it is very easy to see that PY equals to Zn minus YZ minus Pn. So PY, the missing side PY equals to Zn, that is 24 here, minus Zy, that is 3, minus Pn, that is also 3. So Py in total is equal to 24 minus 3 is 24 minus 6. So Py equals to 24 minus 6, that is 18. If we already found out that the missing side Py is equal to 18 units in its length. This is the missing side Py is equal to 18 units in its length. We extended the radius GQ by a straight line, and the result is GT. When you extend a straight line by a straight line, the result must be a straight line. So GT is also a straight line. Previously, we extended the radius NP by a straight line, and we got NZ. And that is the reason that NZ is also a straight line. Here we extended the radius GQ, that is a straight line, by a straight line, and the result is GT. And therefore GT is also a straight line. And we already found out that GT equals to 7 units. Here GT equals to 7 units, so actually GT, that is 7, GT equals to 7 units in itself in total, minus GQ, that is the radius, that is equal to 3 units, minus YT, that is also equals to 3 units. In total, GT minus GQ minus YT equals to the missing side QY. Repeat again. The missing side QY equals to GT minus GQ minus YT. So QY equals to GT, that is 7, minus GQ, that is 3, minus YT, that is also 3. So QY in total equals to 7 minus 3 minus 3, 7 minus 6, that is 1. So actually found out that the missing side QY here is equal to 1 unit in its length. And we only found out that PY equals to 18 units in its length. In the next step, I repeat again that we extended the radius GQ by a straight line, and the result is GT. GT must be also a straight line. So if we focus on this side of the straight line, GT at point Q, the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So at this side of the straight line GT at point Q, the sum of the angles must be equal to 180 degrees according to the rule that I mentioned. So which angles we have at this side of the straight line GT at point Q? We have this angle that is equal to 90 degrees plus this missing angle. In total, they must be equal to 180 degrees according to the rule that I mentioned. So the missing angle here must be equal to 90 degrees. And we already found out that this angle is also equal to 90 degrees according to rule number 1. DC is one side of rectangle ABCD, therefore it is absolutely a straight line. So if we focus on this side of the straight line DC, at point Z, here the sum of the angles must be equal to 180 degrees according to the rule that I mentioned. So which angles we have at this side of the straight line DC at point Z? We have this angle that is equal to 90 degrees, plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees. Therefore, this missing angle must be also equal to 90 degrees. So actually, inside quadrilateral QKZY, we have 1, 2, 3 right angles, therefore the fourth angle here must be also equal to 90 degrees in its size. Repeat again that we extended the radius NP by straight line, and the result is NZ. Therefore, NZ must be also a straight line. So if we focus on the upper side of the straight line NZ at point Y, here at the upper side of NZ at point Y, the sum of the angles must be equal to 180 degrees according to the rule that I mentioned. So which angles we have at the upper side of the straight line NZ at point Y? We have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees. Therefore, this missing angle must be also equal to 90 degrees. And because of the fact that angle QYP, this angle equals to 90 degrees, it means that angle QYP is a right triangle. So we will implement the Pythagoras theorem of the right green triangle, triangle QYP. So copy the right green triangle QYP in a new page, and we will implement on it the Pythagoras theorem. Okay. Okay. This is the right green triangle, triangle QPY that I copied from the original drawing. Side QY equals to 1 unit in length, side PY equals to 18 units in length, and this angle equals to 90 degrees according to rule number 2. So in the right triangle, by PT is a abbreviation for Pythagoras theorem, in the right triangle QPY according to the Pythagoras theorem, we'll get that QP square equals to QY square plus PY square. So QP square, that is the square of the hypotenuse, equals to QY square. QY is 1, therefore QY square is 1 square, that is 1, plus PY square. PY is 18, therefore PY square is 18 square, that is 324. So in conclusion, we found out that QP square, that is the square of the hypotenuse, equals to 324 plus 1 is 325. We take a root out of this equation and we get that QP equals to the square root of 325. But 325 is 25 times 13. Here we can take 25 out of the root. We know that the square root of 25 is 5. So inside the root we left only with 13. In conclusion, we found out that the distance between the centers of those two circles, that is to say, the length of this line segment QP, is equals to either 5 times square root of 13 units, or in terms of numbers, the distance UP, that is the distance between the centers of those two circles, is equal to 18.03 units. Okay? So in the next step, I'll summarize the lecture. In this lecture, we found out the distance between the centers of those two circles, that is to say, the length of this line segment QP. Q is the center of this circle and P is the center of this circle. And the distance between the centers is also QP. In addition, we know that in the drawing we have rectangle ABCD. Side AB of this rectangle is equal to 7 units in its length, side BC equals to 24 units in its length. Again, our mission is to point out the distance between the centers of those two circles, that is to say, the length of this line segment QP. So because of the fact that ABCD is a rectangle, it means that all those 4 angles are right angles, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side DC, but AB is 7, therefore DC must be also equal to 7 units in its length. Likewise, according to the sum rule, side BC equals to side AD, but BC is 24, therefore AD must be also equal to 24 units in its length. Then we focus on the right triangle, triangle ABC, and we implemented the Pythagoras theorem on this right triangle, triangle ABC. According to the Pythagoras theorem in the right triangle, triangle ABC, AC square equals to AB square plus BC square. Repeat again. In the right triangle ABC, by PT is the evaluation from Pythagoras theorem, AC square equals to AB square plus BC square. So AC square equals to AB square. AB is 7, therefore AB square is 7 square, that is 49. Plus BC square. BC is 24, therefore BC square is 24 square, that is 576. So in total, AC square equals to 49 plus 576 is 625. We took out of this equation when we found out that AC equals to the square root of 625, that is 25. So the length of the hypotenuse AC is 25. Then we found out a general formula for the radius of any circle that is blocked by the right triangle ABC. According to our definition, the radius of this circle is equal to x, and we actually succeeded to find out a new formula for the radius of this circle that is equal to x. So the radius of this circle is succeeded to express the radius of this circle only by the side lengths of this right triangle, triangle ABC. Side AB of this triangle equals to units in itself, side BC equals to units in itself, and the length for the hypotenuse of the right triangle ABC, AC equals to 3 units in itself. Here, we define the point of tendency of tangent BC with this circle as M. The radius OM is drawn to point M, therefore according to rule number 1, this angle equals to 90 degrees and this angle equals to 90 degrees. We define the point of tendency of tangent AB with this circle as M. The radius ON is drawn to point N, therefore according to rule number 1, this angle equals to 90 degrees and this angle equals to 90 degrees. So inside quadrilateral ON BM, we have 1, 2, 3 degrees, therefore the fourth angle must be equal to 90 degrees, therefore inside quadrilateral ON BM, we have 4 degrees, therefore we can relate to this quadrilateral ON BM as a rectangle. We also know that the opposite sides of a rectangle are equal to each other, that is to say ON equals to BM. But ON is x, therefore BM must be also equal to x. Likewise, according to the same rule, OM equals to NB, but OM is x, therefore NB must be also equal to x. So actually found out that quadrilateral ONBM is not a rectangle but a square, while because all of its sides are equal to each other, each side of this square is equal to x. Here, AN equals to AB minus NB. This is to say AN equals to AB, that is x, minus NB, that is, again, AN equals to AB that is A minus NB that is X. So in total, AN equals to A minus X. From the dome, it is very easy to see that CM equals to CB minus MC. So that is to say CM equals to CB that is B minus MC that is X. So in total, CM equals to B minus X, and we already found out that AN equals to A minus X. Okay? Then we find the point of tendency of tangent AC with this circle as S, and then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. We have the common standpoint point P. From the common standpoint point P, we have two tangents to the circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say PA equals to PB. So we can implement rule number 2 in our drawing. From the common standpoint point A, we have two tangents to the circle, tangent AN and tangent AS. And according to rule number 2, they are equal to each other. That is to say AN equals to AS. But AN is A minus X, therefore AS must be also equal to A minus X. Then we focus on the common standpoint point C. From the common standpoint point C, we have two tangents to the circle, tangent CM and tangent CS. And according to rule number 2, they are equal to each other. That is to say CM equals to CS. But CM is B minus X, therefore CS must be also equal to B minus X. The hypotenuse AC of the right triangle ABC equals to 3 units in itself according to our definition. But the hypotenuse AC is also equals to AS plus SC. So we can write down that C equals to AS plus SC. AS is A minus X and SC is B minus X. So in total C equals to A minus X plus B minus X. So C equals to A plus B minus X is minus 2x. So in total C equals to A plus B minus 2x. We added 2x to this equation and finally found out that 2x plus C equals to A plus B. We subtracted C from this equation and we found out that 2x plus C equals to A plus B. And then we subtract C from this equation and found out that 2x equals to A plus B minus C. Then we divided this equation by 2 and found out that x equals to A plus B minus C over 2. So the radius of x of this circle equals to A plus B minus C over 2. We can implement the new formula in order to find out the radius of this circle. According to the radius of this circle that is blocked by the right triangle ABC. The radius R of this circle must be equal to AB plus BC minus AC over 2. Repeat again. The radius R of the circle equals to AB plus BC minus AC over 2. So R equals to AB that is 7 plus BC that is 24 minus AC that is 25 over 2. 7 plus 24 is 31, 31 minus 25 is 6 and 6 over 2 is 3. So found out that the radius of this circle that is blocked by the right triangle ABC is equal to 3 units in length. Then we found out the radius of this circle that is x according to our definition. The radius this circle is blocked by the right triangle CDA. According to the new formula, the radius x of this circle must be equal to CD plus DA minus CA over 2. Repeat again. The radius of the circle equals to CD plus DA minus CA over 2. CD is 7, DA is 24, minus CA that is 25 over 2. 7 plus 24 is 31, 31 minus 25 is 6, and 6 over 2 is 3. So if we know that the radius of this circle x also equals to 3 units in its length. Okay. Then implemented the rule number 1. PM is the radius of this circle that is equal to 3 units. The radius PM is drawn to point M, therefore according to rule number 1, this angle equals to 90 degrees and this angle is also equals to 90 degrees. The radius PN is drawn to point N, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. That is to say this angle equals to 90 degrees, this angle equals to 90 degrees according to rule number 1. So inside quadrilateral PNBM we have 1, 2, 3 degrees, therefore the fourth angle must be also equal to 90 degrees. Therefore, inside quadrangle PNBM, we have 4 right angles. Therefore, can relate to this quadrangle PNBM is a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, PN equals to BM. But PN is 3, therefore BM must be also equal to 3. Likewise, according to the sum rule, PM equals to NB. But PM is 3, therefore NB is also equals to 3. So we can find out that PNBM is not a rectangle, but a square, because of the fact that all of its sides are equal to each other. Likewise, if we repeat on the same process, here we get that KQGD is also a square. Each side of this square is equal to 3 units in its length. Then we extended the radius GQ by side line until it touches side BC of the rectangle at point T. In this way, we created quadrangle TC GD. Inside this quadrangle, we have 1, 2, 3 angles, therefore the fourth angle must be also equal to 90 degrees. So inside the big quadrangle GT TC, we have 4 angles. Therefore, can relate to this quadrangle GT TG GDTC as a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. That is to say, DG equals to TC. But DG is 3, therefore TC must be also equal to 3 units in its length. Likewise, according to the sum rule, in rectangle DGTC, side DC equals to side GT. But DC is 7, therefore GT must be also equal to 7 units in its length. Here GT equals to 7 units. In the next step, we extended the radius NP by side line until it touches side DC of the rectangle at point Z. Inside quadrangle NBCZ, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Therefore, inside quadrangle NBCZ, we have 4 right angles. Therefore, we can relate to this quadrangle NBCZ as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, NB equals to CZ. But NB is 3, therefore CZ must be also equal to 3 units in its length. Likewise, according to the sum rule, BC must be equal to NZ. But BC is 24, therefore NZ must be also equal to 24 units in its length. Then we define the intersection point here as point Y. And so actually, inside the small quadrangle YZTC, we have 1, 2, 3 angles, therefore the fourth angle must be also equal to 90 degrees. Therefore, inside quadrangle YZTC, we have 4 angles. Therefore, can relate to this small quadrangle YZTC as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, TC equals to YZ, but TC is 3, therefore YZ must be also equal to 3. Likewise, according to the sum rule, in the small rectangle YZTC, ZC must be equal to YT. But ZC is 3, therefore YT must be also equal to 3. So actually found out that quadrangle YZTC is not a rectangle but a square. Why? Because all its sides are equal to each other, its size is equal to 3 units. Then we found out that PY equals to NZ minus PN minus YZ. Again, PY equals to ZN minus YZ minus PN. So PY equals to ZN, that is 24, minus YZ, that is 3, minus PN, that is 3. So in total, PY equals to 24 minus 6, that is 18. PY equals to 18. What is the length of the missing side QY? QY equals to GT, that is 7, minus GQ, that is 3, minus YT, that is 3. Repeat again. The missing side QY equals to GT minus GQ minus YT. So QY equals to GT, that is 7, minus GQ, that is 3, minus YT, that is also 3. So QY in total equals to 7 minus 6, that is 1. Yeah. QY equals to 1 unit in its length. Then GT is a straight line because when you extend the radius GQ, that is a straight line by straight line, the result GT must be also a straight line. So we focus on this side of the straight line GT at point Q. Here the sum of the angles must be equal to 90 degrees. So which angles we have here? We have this angle is equal to 90 degrees plus the missing angle in total must be equal to 180 degrees. Therefore the missing angle must be equal to 90 degrees. We have already found out that this angle equals to 90 degrees according to rule number 1. Then we focus on the straight line DC. This side of the straight line DC, point Z. Here the sum of the angles must be equal to 180 degrees. So which angles we have? We have this angle is equal to 90 degrees plus the missing angle in total must be equal to 180 degrees. Therefore this missing angle must be equal to 90 degrees. So I actually found out that inside quadrant QKZY we have 1, 2, 3 angles. Therefore the fourth angle must be also equal to 90 degrees. Then we focus on the upper side of the straight line ZN at point Y. Here the sum of the angles must be equal to 180 degrees. So which angles we have here? We have this angle that is equal to 90 degrees, but the missing angle in total must be equal to 180 degrees. So this missing angle must be equal to 90 degrees. So if this missing angle QYP equals to 90 degrees, it means that the right triangle QYZ, the great triangle QYP, is the right triangle. So I copy the right great triangle QYP in a new page and represent the Pythagoras theorem in this great right triangle QYP. This is the right triangle QYP that I copied from the original drawing. QY equals to 1 unit, PY equals to 18 units. So according to the Pythagoras theorem, QP square equals to QY square plus PY square. So QP square equals to QY square. QY is 1, therefore QY square is 1 square, that is 1. Plus PY square. PY is 18, therefore PY square is 18 square, that is 324. So in total QP square equals to 1 plus 324, that is 325. We took out of this equation and found out that QP equals to the square root of 325. But 325 is 25 times 13. Now we can take 25 out of the root. The square root of 25 is 5, so in conclusion we found out that the distance between the centers of those two circles QP equals to either 5 times square root of 13 units, or in terms of numbers, it is equal to 18.03 units. QP equals to 18.03 units. Okay, thank you very much.